towards automated verification IP instantiation via LLMs. That's right. Recent advancements in the large language models (LLMs) have opened a new possibility for automation in hardware verification, including tasks such as generating formal assertion from the natural language specification and the real register transfer level RTL implementations. However, despite these promising developments, current LLM-generated assertions often fall short of the human-level quality, limiting their practical use in formal verification workflows. On the other hand, verification IPs or VIPs are the comprehensive and incorporating a complete set of the checker that systematically validate different aspects of the design under test. However, deploying the VIPs has traditionally been challenging for designers due to limited understanding and the time constraint, which can lead to delays and increase the risk of missed bugs. To address these issues, our work introduced LLMs as both assistants and an agent for automating VIP instantiation, specifically designed to aid verification engineers. Our solution overcomes existing VIP deployment challenges by streamlining and automating the integration process, providing detailed guidance on VIP usage and optimizing the resource application allocation and key advantage for meeting the tight project timeline. Our results demonstrate in the retrieval augmented generation RAG enabled robust interpretation of Verilog RTL and producing the synthetic and logical sound VIP instantiations essential for maintained verification integrity. Chapter 1 in the introduction. Formal verification accounts for an average 56% of the time spent on ASIC design and plays a critical role in the design process in verifying the correctness of the chip design. While the FPG formal verification provided notable benefits such as catching elusive bugs that may be missed in science simulation-based method. It also has a limitation. Formal verification workflows demand significant engineering effort to develop the formal test benches manually and supporting collateral, a task handled by skilled experts. This requirement makes it challenging to scale FE formal verification adoption and expand its coverage across a large number of the subsystems. Recent advancements in large language model LLMs have led researchers to explore their potential for automating and enhancing productivity in hardware verification. Specifically, recent studies have examined the use of LLMs for testing formal verification, such as generating formal assertions from a natural language and NL. So the specifications and from the registered transfer level RTL descriptions of the design under test DUT and the rationale behind this exploration is clear. The input handled by a human formal verification engineer, such as the design RTL specification, and the outputs they generate, formal verification test bench implementations, are inherently represented as text and code, which aligns well with the LLM's strengths in reasoning and content generation. Although the prior work has demonstrated that LLMs can indeed generate hardware assertions, the quality of these assertions remains limited to falls short of the human-level expectation. Due to this limitation, using LLMs for such task is not yet viable for verification teams. Many verification teams have developed verification IPs, and by packaging the most frequently used the verification checkers to facilitate reuse across the project and enable deployment by engineers who are not the verification experts. VIPs enhance productivity by enabling engineers to verify design compliance with various protocols and standards effectively. However, the deployment of the VIPs has been fraught with challenges. such a tight project schedules or a lack of the expertise regarding the optimal use of each VIP. A more effective solution of automating common VIP instantiation by exploiting patterns of the common modules has immense potential in ensuring thorough coverage and rapid development for new projects. Greatly accelerating the verification process and chip production. Our main novel contribution to this work are data processing pipeline for the large Verilog code files. A novel data processing pipelines is proposed to manage large-scale Verilog code files effectively, facilitating the creation of optimizing prompt for LLMs. The pipelines begins with cleaning the RTL system Verilog code to remove the unnecessary elements, followed by the segmenting the code into manageable chunks. A key innovation in this pipeline is the method to process these chunks in a manner that minimizes the LLM agent calls, thereby optimizing the runtime performance. Additionally, a multi-threading approach is integrated into the pipeline to handle the large RTL files with the numerous VIP instantiations efficiently. This ensures that the system can scale to meet the demands of complex verification tasks involving the substantial code bases. LLM-based automation of VIP instantiation. An LLM-based flow is developed to automate the instantiation of various verification VIPs, and streamline the verification process. With this flow, the multiple augmentation method were explored to optimize the LLM performance. The in-context running (ICL), this method enhanced the LLM responses by including demonstration within the prompt, enable the model to infer mechanism to generalize them to the new queries. While effective in improving the accuracy, ICL requires extensive prompt engineering and becomes rigid and unscalable when applied to diverse VIPs. Retrieval augmented generation (RAG) to address ICL's limitations, a RAG-based approach is introduced. RAG consists of two key steps. First is constructing a vectorized database of knowledge chunks derived from prior VIP examples. Second, employing the retrieve function to extract the most relevant knowledge based on the user query. These retrieved chunks are appended to the LLM prompt, embedding specialized knowledge into response without requiring additional model training. This flexible and cost-effective method enhances the adaptabilities of the LLM for various verification contexts. Post-response data correction and hallucination detection. A post-response data correction pipeline is designed to ensure the reliability and precision of LLM-generated output. This pipeline identifies and corrects the inconsistency in the generated content, mitigating the risk of the errors in the VIP instantiation. Furthermore, a hallucination detection mechanism is implemented to identify the flag instantiation where the LLM-generated content that deviated from the expected over the factual basis. Together, these components enhance the overall robustness and accuracy of automated verification flow. Chapter 2 is the preliminaries. Formal hardware verification. Hardware verification is a critical phase in a chip design process essential for ensuring that the final product performs according to its specifications. Despite the increasing allocation of resources to verification compared to the hardware design, recent industry data indicated a growing number of projects where critical bug evaded detection during the verification, requiring the costly spins to address them. Two primary approaches to hardware verification are widely recognized: traditional simulation-based verification and formal verification, which has gained considerable traction over the past decade. Unlike a simulation-based method, formal verification seeks to rigorously prove the digital circuit design adheres to a specified set of the requirement. So in formal verification, the specification is defined by a set of the properties constraining the search space, assumptions, or identifying the design expected behaviors, assertions. So the digital circuits are well suited to representation as state transition systems, while the properties are expressed in temporal logic. This setup enables model checkers to transfer the state transition graph, searching for any state that violates these properties. When a model checker identifies such a state, it provides a counterexample or trace that shows where the property fails. In contrast, simulation-based verification tests properties only for a subset of states based on a specific input stimuli. If a model checkers can demonstrate that property holds across all states, it effectively provides a formal proof that the property is universally valid for the design. The B is RAG, Retriever Augmented Generation. Retriever Augmented Generation, RAG, shown in Figure 1, is cutting-edge and computationally efficient method that enhances the LLM's responses by drawing from specialized vector database of external knowledge. To set up the RAG, a vector database must first be created and storing the knowledge corpus as semantic vectors. This corpus can consist of various document types, such as web pages, PDFs, and text files. To accommodate the storage requirement, each document is broken into smaller, manageable chunks that adhere to a token limit. Building this vector database is on time the process, although it can be refreshed as new documents are added or existing ones are updated. Once the vector database is prepared, the log system is ready for querying. When a user poses a question to the RAG system, it first converts the query into a semantic vector, and the log then retrieves the top k chunks from the vector database that are most relevant to the user query. At a high level, this process is performed by calculating the similarity index between the query and each of the chunks that come from the specialized RAG database. These selected chunks are appended to the user's query, and which is passed to the LLM for the responses generation. Consequently, the LLM's answer is enriched the precise information from the RAG vector database, and producing the responses that are both accurate and contextually informed. The Figure 1 is general for retriever augmented generation. Question, retriever augmented question passed to the LLM generation and explicit resource informed in the answer. Chapter 3 is motivation, the prior work. In this paper, we introduce a novel application of the large language models LLMs as agents for the automatic instantiation of verification intellectual properties, VIPs, a topic that remains unexplored in formal verification research. Prior work has evaluated LLMs for the tasks such as system Verilog assertion, SVA's code generation, and assertion generation with the assertion LLM, in both demonstrating promising result in generating functional and high-quality code. However, in practical settings, the VIPs serve as effective checkers to verify the repeated RTL register transfer level modules, containing the numerous assertions that are crucial to validating module correctness. The potential benefits of automating VIP instantiation across different designs are substantial, motivating us to explore the agent-based approach in which an LLM is trained specifically as an expert for VIP instantiation. This approach aligns with the growing trend of the optimizing LLMs for specialized domains to enhance accuracy and reduce hallucinations, focusing their capabilities within a narrowly defined area. Using a generic out-of-the-box LLM such as a GPT model or Meta Llama 2 and 3 is inadequate for our objectives. Nor do internal LLMs currently have a necessary proficiency for targeted VIP instantiation. This limitation stems from the absence of the VIP-related data in the model's pre-training dataset. In other words, foundation LLMs lack the specific knowledge needed to understand and instantiate VIPs accurately, while fine-tuning LLMs to integrate the formal verification knowledge related to VIPs could address this gap. Generating new datasets and fine-tuning models is both time-intensive, often taking weeks, and computationally costly. Thus, fine-tuning becomes an impractical solution for scalable VIP instantiation, highlighting the need for approaches that are efficient, cost-effective, scalable to future iteration of automatic VIP instantiation project. So, a significant challenge remains without fine-tuning. The LLM lacks any inherent knowledge of our specialized for verification VIP instantiation task. One possible approach is to include all necessary information for VIP instantiation directly in the query. However, LLMs have a limited token text window. For instance, Rama 2 has a context window of 2048 tokens, meaning the combined length of the prompt and the response must not exceed this limit. Else the response is truncated, leading the incomplete or inaccurate VIP instantiation. This constraint presents a bottleneck when working with large files, as we must carefully manage the information passed to the LLM to avoid wasting valuable tokens on irrelevant details. To maximize the effectiveness of the LLM within these limitations, it's essential to ensure that only most pertinent information is provided, specifically tailored to the VIP type being instantiated. Developing a strategy to handle large files efficiently allows us to streamline VIP instantiation by including only necessary context, thus avoiding truncation issues and ensuring that LLM's tokens windows is utilized optimally. This approach is critical for accurately instantiating VIPs across different designs while maintaining efficiency and effectiveness within the constraint of the LLM's token limit. Existing research offers two promising methods for equipment LLMs with the relevant information needed for effectively address challenges like those discussed here, especially the limited context window. This method, known collectively as prompt augmentation, including in-context learning ICL and retrieval augmented generation RAG, rather than retraining an LLM, both methods build upon an out-of-the-box model, enabling a quicker implementation and alignment for the LLM agent with our domain-specific needs. Furthermore, as outlined in the previous section, RAG facilitates straightforward database creation and eliminates the need for the prompt structure modifications. Adding information to the vector database is sufficient to introduce new specialized VIP knowledge to the LLM. Chapter 4. LLMs as Assistant and Agent. Our work to introduce LLMs as agent driving the instantiation of VIPs for verification engineers. Our proposal outlines the procedure to take a state-of-the-art foundational LLMs and apply them to the focused and technical domains to accomplish tasks with performance far exceeding those of base LLMs. Through retrieval augmented generation (RAG), we have successfully deployed a special Q&A bot for design and verification engineers that augment its natural language reasoning with the domain expertise from VIP documentation, details in Figure 2. However, the focus of this proposal is on VIP instantiation, where we present our modularized, scalable pipeline that allows for the instantiation of VIPs We demonstrate in our experiment in ROG provide a more robust understanding of the verification Verilog code compared to our baselines, creating fewer hallucinations and exceedingly accurate and precise result necessary for the proper generation of VIP instantiation to be deployed in forward verification pipeline. Here are some example questions, but you can ask your own. Figure 2 is displayed Q&A chapter based on the ROG to help answer engineers' queries on VIPs. Give me a list of all VIPs available to use. What is a VIP for Creative Valley interface? What is a VIP for Great Code? How to use valid credit VIP. Instantiate the valid credit VIP for SCC to CSN underscore REQ underscore the credit interface. What is a VIP for the safety? Chapter 5 Method. The proposed VIP instantiation flow is divided into 4 main steps: data preprocessing, prompt augmentation, a VIP instantiation, and an LLM output post-processing as shown in Figure 3. In the following section, the details of each stage will be explained. A. RTL code preprocessing pipeline. The first data preprocessing stage involves 2 main tasks: filtering the raw RTL design files and then partitioning code into sizable blocks for prompt to the LLM. For the first step of cleaning the RTL design files, we have a deterministic algorithm containing procedure to filter out unnecessary artifacts from the code that are irrelevant to VIP instantiation. These artifacts include comment, if and if declaration, input or output port declarations with keyword defined and includes and blank lines resulting from deleting these details in the code files. So the following filtering these details, we are ready to process the cleaned code file into prompt. The second step, which is partitioning of the code blocks, is performed using our Naval algorithm to ensure optimal chunking by maintaining the integrity of blocks of code while respecting LLM token limit. This step is crucial to formulate the raw data into reasonable prompts so we can leverage LLMs in our flow with minimal hallucinations. To do so, we use our proprietary algorithm that recursively split cleaned Verilog code into partitions that obey a maximum token count. We must respect to query the target LLMs accurately. This step aims to ensure each query to LLM contains a partition of a cleaned code file that is statically complete so we can process each section independently to the LLM and instantiate relevant VIPs using cleaned information. We have verified our data pre-processing technique work reliable for our instantiation of FIFO and arbiter VIPs and designed our algorithms to cover cases for these modules. However, our data pre-processing pipeline, along with the rest of our flow, was designed to scale the implementation to any number of VIPs, which we have done by adding to the list of rules we want to be followed in the driver functions of our cleaning and prompt creating processes. The execution of these steps results in the cleaned prompts of a partitioned code that we can iteratively feed to our LLMs to instantiate our VIPs. The code partitions have no overlap and collectively span the entire cleaned code file. So next is B, prompt augmentation. The second stage of our VIP instantiation flow is the prompt augmentation stage, which we vary in method depending on the experiment we conducted to determine the efficiency of retrieval augmented generation RAG in instantiating VIPs compared to our baseline and in context learning ICR method of prompt augmentation. We set up our RAG vectorized database to contain the internal documents and VIP instantiation and examples of module code and VIP instantiation pairs, demonstrating the example of a proper VIP instantiation. Each experiment involved the LLM being iteratively fed each base prompt created from the data preprocessing stage. For baselines augmentation, we feed just code the partition without a further augmentation of the evaluating VIP instantiation to the LLM as a controller. For the ICL and the RAG experiment, we developed a distinct series of rules format verification experts would use to help instantiate VIPs for FIFO arbiters. If a FIFO is detected inside a code partition, our flow will attend the FIFO rule set. If an arbiter is detected, the arbiter rule set will be appended to the guide LLM according to these different rules modules. This rule set remained in the same between the ICL and the RAG experiment and were appended after each code partition to augment the response. The ICL method prompts were also given a one-shot example of the VIP instantiation for respective module, while the RAG method used the RAG to augment the prompt with relevant chunks from the vectorized database of internal document on formal verification. After the steps in prompt augmentation, the finalized prompts are ready to be fed through the LLMs to be queried for VIP instantiation. C is a proposed LLM-based flow for VIP instantiations. The third stage involved VIP instantiation through the LLM agent, where the augmented prompts are iteratively queried to generate the desired VIP instantiation for each respective code partition. This stage leverages the deployed augmentation method to enhance the prompt and guide the LLM toward the accurate efficiency VIP instantiation. Context learning method. In this approach, the deployed prompt incorporates a general system prompt held for each target VIP, such as the FIFO or the arbiter VIPs. This prompt includes a set of the general rules to instruction the LLM on how to instantiate the VIP, supplemented by a specific instruction derived from experimental observation. For the flow then combines these elements into final prompt, integrating the in-context learning ICL component with the RTL code chunk. This ensures that the LLM generated VIP instantiate the adhered best practices and the requirement identified during the early stage of experimentation. The retriever augmented generation RAG method. For this method, the process beginning by identifying the target VIP to instantiate relevant examples and details are retrieved from the knowledge vector database using the RAG approach. This extracted elements are appended to the initial prompt for specific RTL code chunk. By incorporating these precise contextually relevant details into prompt, the LLM's prompt is enriched to producing responses that are not only accurate but also well informed by prior knowledge stored in the RAG vector database. This approach enhances the overall reliability and quality of the VIP instantiation process. The LLM used for both baseline and ICL experiment was a Llama model fine-tuning on internal code documentation, including Verilog code. For the RAG, we used the open source Llama 3 70-bit instruction in endpoint, giving the additional value to the RAG approach for VIP instantiated by demonstrating expensive fine-tuning the domain is not necessary for the correct VIP instantiation. Calling the LLM for each partition of the code is costly in many cases, as some of the Verilog files we performed our experiment on contained hundreds of thousands of lines of code, making the aggregated inference time hours. We optimized the runtime bottleneck by creating a method to identify or create appropriately greater probabilities partition of the code contained the desired FIFO and arbiter modules and only processed these chosen chunks. These help methods are designed to use naming the convention of the FIFOs and the arbiters. We can strongly assume former verification engineers follow their coding syntax and ignore all chunks that now have any major instantiation of four FIFOs and arbiters. This function ensures every FIFO and arbiter will be processed, but false positive can occur where an LLM receives the code partition, hallucinates and instantiates the anonymous VIPs for the misidentified module instantiation. These false positives are easily detected in post-processing following the completion of LLM queries. Aggregated output results are ready for the final post-processing stage of the flow. These results post-processing pipeline. The fourth of the final stage of VIP instantiation flow is post-processing the LLM VIP instantiation. Here we augment the filter the LLM output response to complete the VIP instantiation. First, we detect false positive by exploiting pattern the outputted response that signal that a response was hallucination. Specifically, in the prompt, LLMs are instructed when a signal needed for the VIP instantiation is not found in the inputted code partition to flag the signal as unknown. For the FIFO and arbiter modules, most of the signal ports are defined in code. Seldom edge cases where a verification engineer needs to identify a signal for a VIP instantiation manually. Two or more unknown signals means the instantiated VIP was a false positive, and we can confidentially avoid the hallucination in the final output. If the false positive are filters, we are left with the VIPs instantiated for their respective identified modules or either a FIFO or arbiter. We developed driving post-processing functions for each module to complete the VIP instantiations and making them valid VIPs. For instance, instantiations of the FIFOs sometimes need additional post-processing to fill in the FIFO depth and data width. These premises a requirement for the VIP to be complete, but these values are sometimes not in the code file. To complete the VIPs, for these cases, we develop an automatic retriever process to extract the FIFO depth and data with four high FIFO modules in module respective source code. The source values are injected into LLM output to complete instantiation, leaving us with a complete and correct VIP instantiation for the file module. Finally, these post-process responses are aggregated and written to an output file and ready to be used in the next part of the formal verification process of verifying the Verilog code. Figure 3 is a proposed LLM-based framework for code generation for VIP instantiation. Stage 1 is data preprocessing, Stage 2 is prompt augmentation, and Stage 3 is LLM VIP instantiation, and Stage 4 is LLM output post-processing. The Chapter 6 is results and discussion. Starting from the RTL Verilog code of our target design, the proposed VIP instantiation flows has been used to instantiate FIFO and arbiter VIPs for several duties. So the table 1 is compare the effectiveness of the three prompt augmentation techniques: baseline, in-context learning (ICL), and retriever augmented generation (RAG), using two distinct LLMs: chip Mistral X by 7-bit chat TP4 TRT H100 and Llama 3 70 billion, and for generating VIP assertions in FIFO and ARB components. A comparison of different prompt augmentation techniques. 1. Baseline. This approach tested with the chip Mistral 8 by 7-bit chat TP4 TRT H100 model was not able to correctly identify and instantiate either of the VIPs. In Table 1, all instances for assert VIP FIFO and assert VIP ARB were marked as missing, indicating that the baseline prompt alone inefficient for generating correct VIP assertions. In context running ICR, when enhanced with ICR, chip Mistral 8 by 7-bit chat TP4 TRP H100 model showed moderate improvement. For assertion underscore VIP underscore FIFO, ICR produced four correct and incorrect produced four correct, one incorrect, and two missing outputs. However, results were less consistent for assertive VIP ARB, with only one correct output, four incorrect, and seven missing instances. While ICR improved performance compared to the baseline, its results were variable, particularly with more complex design. The retriever augmented generation RAG. This method delivered better performance for FIFO VIP, assert underscore VIP underscore FIFO. A RAG produced 7 out of 7 correct outputs, achieving a 100% accuracy rate. For arbitrary VIPs, assert underscore VIP underscore ARB. RAG generated 11 correct outputs with only one incorrect, showing the strong reliability across both VIP assertion tasks. B. Comparison of the performance difference LLM models. Chip Mistral 8x7-bit tested with both baseline and ICR prompt augmentations. This model struggled to deliver consistently accurate output. This baseline approach yielded non-correct result, while ICR shows some improvement with limited success, particularly in generating assertive VIP FIFO assertions. However, its overall performance was inconsistent, especially for more complex assertive VIP ARB tasks. Llama 3 7-bit with RAG. The Llama 3 70-bit model paired with the RAG substantially outperformed the Chip Mistral 8x7-bit chat in both assertion tasks, which achieved perfect accuracy for assertive VIP FIFO and nearly perfect result for assertive VIP ARB. This suggested the Llama 3 7-bit, particularly with the RAG, has a stronger capability in generating accurate and reliable VIP assertions, demonstrating its suitability for complex verification tasks. In summary, the RAG retriever process provides a far greater benefit for the overall accuracy of instantiation compared to the baseline ICR method, with a few short runnings and demonstration in table below. Additionally, because the RAG method used an open-source Llama 3 endpoint instead of a fine-tuned chip model trained on internal data, including not rely on the fine-tuning models to execute each task, meaning that we can update our procedure with better LLMs that only improves our VIP instantiation solution. In other words, our flow is designed to match the pace of ongoing LLM research and to be updated with the inference capability of the latest, strongest LLMs in the industry. Furthermore, due to our modularized procedure, our LLM-powered VIP instantiation process has a potential to support many more VIPs fast developing and is applicable beyond any project. Table 1, result of the VIP instantiation for both assertive VIP info and assertive VIP ARB. Key references. There are so many references, 1 to 24. Okay, today I read this paper, the two words, automated verification IP instantiation via LLMs, from DVCON2025. Thank you for your time. See you next time.